This is P3 continued. So here we see a number that is the nth power of a rational number is called a perfect nth power. For example, 27 is a perfect third power or perfect cube because base 3 to that power of 3 or cubing is equal to 27. So we say 27 is a perfect cube. It would be a 3 by 3 by 3. Just like we know with perfect squares. 4 is a perfect square because 2 squared equals 4. Now, when we're finding nth roots of perfect nth powers, you really have to look at the radical that you're given and determine if the index or the root is odd or if it's even. Okay? Your college algebra is going to do a lot with odd and even in throughout the textbook with other topics. Okay, so this idea of odd and even is going to keep coming back up. Now, if I have the nth root of a to the nth power, that's going to equal a itself. You see, because the n here, the index, and the n here, the exponent, they're going to be the same, okay? And so it's going to equal the radicand, or a that's inside the radical. If n is even, however, the nth root of a to the nth power is equal to the absolute value of a. You must use the bars. And that brings me back to when we were looking at this. Okay, this particular example. When we simplified something like this in radical form. So we got it down to here, okay? We knew that we had an r squared on the outside times the square root of rs divided by the square root of s to the power of 6. And we knew we could simplify this more because 6 was even, so s to the power of 6 is a perfect square. So now, it's an even root, square root, and an even exponent, power of 6. You can't just say this equals s to the power of 3. It's the absolute value. Because remember, if s is negative, when I substitute it back in here, it's going to be positive, right? Like negative 1 to the power of 6 is positive 1. But if I put that same negative 1 here, negative 1 to the power of 3 is negative 1. So you need the bars to ensure that the two expressions are, in fact, equal for every value of that variable. Okay, so keep that in mind. It's the even roots that are going to give us some issues. So, when are we going to see this? Well, for example, notice here, cube root of something to the third power, okay, cubing and cube rooting, okay, they're inverses of one another. That's going to equal negative 4. Because when I take negative 4 and raise it to the third power, I'm going to get negative 64, and the cube root of negative 64 is negative 4. Here's when the index is even. Okay, they're both even here. So the fourth root of negative 7 to the fourth power does not equal negative 7. It equals positive 7. It equals the absolute value of negative 7. If you have any questions about that, you can ask in class. Moving on with this part of the notes, we have the product and the quotient rules for nth roots. We saw the product and the quotient rules work for square roots. And in fact, the product and the quotient rules are going to work for any root. We use n to denote that this could be any number greater than or equal to 2. Okay, so this could be 5th root. It could be 12th root. Of course, we need to put a disclaimer here that b cannot equal 0 since b is in the denominator and division by 0 is undefined. Now, on this next page, it does say here to see page 31 study tip. And in fact, I took a little bit of time and wrote out what the study tip was. And pretty much basically, you're going to see here that some higher, even, and odd roots occur so frequently that you're going to want to memorize them. It just makes sense for you to just go ahead and memorize them. You know, if we're looking at perfect cubes, 1 is a perfect cube, 8 is a perfect cube, 27 is a perfect cube, 64 is a perfect cube. Okay? And when we say cube, we mean an actual cube, like an ice cube, a three-dimensional object. a 4 by 4 by 4 would give me a volume of 64, hence the reason why 64 is a perfect cube. And then, of course, here, 125, that's also a perfect cube. These occur so frequently. Your perfect fourth powers are 81 and 16. Those are the ones that occur the most. And then, of course, your perfect fifth powers, 32 is the one that occurs the most. So you want to keep those in mind when you're looking at numbers and, processing what you could do, how you can simplify things. It benefits you to know what those perfect nth powers are. Of course, remember that 1 is a perfect any nth power, right? The fourth root of 1 is 1. The fifth root of 1 is 1. The 100th root of 1 is 1, and so on. All right, so simplify the following. I have the answers already written out here for you. So I'm just going to talk about it. 64 is a perfect cube. And so the cube root of 64 is 4. Cube root of 40. Folks, you have to break this down. 40 is not a perfect cube, but there is a perfect cube factor that does divide 40. 8 is that perfect cube that divides 40. So I could rewrite 40 as 8 multiplied with 5. Since the 8 is a perfect cube, it comes out as a 2. And my final answer here in simplified form is 2 times, or multiplied with, the cube root of 5. Make sure that you are using the index, okay? Don't write 2 times the square root of 5. Square root and cube root are not the same thing. This one here is the fifth root, okay? If you notice, I'm going to do 8 times 8 because I'm going to use that product rule. So the fifth root of 8 times the fifth root of 8 is equal to the fifth root of 8 times 8, or 64. I know that 32 is a perfect fifth power, and it divides 64 by 2. Okay, and so I can rewrite 64 as 32 times 2, show that the fifth root of 32 equals 2. It comes on the outside. And so that one stays on the outside, and this one stays on the inside because 2 is prime. Final answer, 2 times the fifth root of 2. This one here, take notice that both 125 and 27 are perfect cubes. So this, I'm simply going to use the quotient rule that says the cube root of a fraction is equal to the fraction of the individual cube roots. And then you simplify it. Okay, combining cube roots. We've seen this with combining square roots when you saw something like this. Okay, so I knew that I had 1, 2, 3, 4, 5, 6, 7, 8 square roots of 5. So I can add them up and write it as 8 being multiplied with the square root of 5. I'm going to do the same thing here. But you have to make sure that the radicands are the same. You know, the cube root of 81 is not the same as the cube root of 3. And so what do you have to do here? You have to simplify. 81 is a square. It's not a cube. Again, be careful that you're not trying to do squares instead of cubes. You have to realize what the index or the root is. Okay, this is 3 times cube root of 81. Subtract 4 times the cube root of 3. I can rewrite 81 as 27 times 3. The 27 comes out as a 3. Now, notice, this 3 and this 3 are both on the outside. This is straight across multiplication. So we've got 3 times 3, or 9 times the cube root of 3. Subtract, this already was in its simplest form. Subtract 4 times the cube root of 3. So 9 of these, take 4 of those same kind away. I'm left with 5 of those kind. 5 cube roots of 3. Okay, same thing here. You have to ask yourself, is 24 a cube? And you say, no, it's not, but 8 is. So we could rewrite 24 as 8 times 3. Take the 8 out as a 2. 3 times 2 is 6. We got 6 cube roots of 3. Plus, notice 27 is a perfect cube. It comes out as a 3. So plus 3 cube roots of 3. 6 of them kind plus 3 more is 9 of those. Here we're going to look at this with variables. Okay, there is subtraction in between. I'm going to break the 24 again into 8 times 3, where 8 is the cube. That's going to come out as a 2. 3 to the power 1 stays in. X to the power 1 stays in. Y to the power of 3 comes out as y to the power of 1. I don't have to worry about absolute value bars because the index is odd. Okay, this one, y was already on the outside. 27 is my cube because 27 times 3 is 81. 27 was the cube that divided 81. It comes out as a 3. So this part of the expression becomes 3y times the cube root of 3x. And since these are exactly the same, this is y cube roots of 3x and another y cube roots of 3x. So if I have 2 of those, take 3 of those same kind away, I'm left with negative 1 or negative y times the cube root of 3x. Okay, moving right along. Remember, this is the instruction video that I'm trying to make be a little bit less time consuming for you to listen to me. And so if you have questions, be sure to ask them in class. All right, rational exponents. I circled the word ratio here because these are exponents that are fractions. They are ratios. A to the 1 over n power, excuse me, becomes a to the 1, that's the power, n is the root. And I can convert this into a radical. N is the root, so it's the nth root of a. 1 is the power, a to the power 1. Now this right here, n greater than or equal to 2 is an integer. That just means the index or the root has to be 2 or more. In other words, it has to at least be a square root. There is no such thing as a first root. Furthermore, if the exponent is negative, you would first put that base in the denominator to change the sign of the exponent, and then you would do the same thing. Of course, a can't be 0 because it's in the denominator. I have a little illustration here. A to the 1 over n. The numerator is the power. The denominator is the root, just like this little drawing here. The flower is the power, and the root is in the bottom. Okay, so whatever it takes to help you remember that with your rational exponents. Power's in the top, roots are in the bottom. Which brings us to 49 to the 1/2 power. Folks, it's power over root. This is the second root or the square root of 49 to the power 1. And the square root of 49 is 7. 27 to the negative 1/3, you're going to move that down to the denominator. And this now becomes the cube root of 27 to the power of 1. And the cube root of 27 is 3, so we replace this value and simplify it into 1/3. This part of the notes, if the nth root of a represents a real number, m over n, that's your rational exponent, is a rational number reduced to lowest terms, and you at least have a square root or more, then we could rewrite this a to the m over n as the nth root of a with the m on the outside of the radical or on the inside. They both mean the same thing and they both do the same thing. Sometimes it's preferred to use one versus the other. The exponent m over n consists of 2 parts. The denominator, n, is the root, and the numerator, m, is the power, which was previously discussed. Furthermore, if you have a negative exponent, take the reciprocal or stick that negative exponent in the denominator to make the exponent positive instead of negative. All right, so what are we going to do with that? We're going to simplify some things like this. So I've got 4 raised to the 3 over 2 power. Remember, it's power over root. So this is the square root of 4 cubed. The square root of 4 cubed. I put cubing on the outside. Why? Because I knew 4 was a perfect square. So I'm like, oh, the square root of 4 is 2. There's the cubing. 2 cubed is 8. You could work it the other way. You could put the cubing on the inside. This is the square root of 4 cubed. Cube of 4, you get 64. The square root of 64 is 8. Either way, you get the same answer. But I will say that I personally like to work with smaller numbers than larger numbers. And 4 was a small base raising to the 3rd power, so this number didn't get so large. But these can get quite large if you put the exponent on the inside of the radical. and do it that way. Okay, the next one, 32 to the negative 2/5. Again, make sure that the exponent is positive. Again, convert to radical form. The 5th root of 32 is 2. I have my squaring on the outside. 2 squared is 4. This one here, you might want to put a little star by this kind. Okay, remember, this is straight across multiplication. Don't try to do any FOIL or anything odd as such. This was kind of like when we did scientific notation. 2 times this x times 5 times this x is the same as 2 times 5, or 10. And this x times that x, same base, add the exponents. So you've got 4/3 plus 8/3. 4/3 and 8/3 is 12/3, and 12/3, of course, becomes a 4. Keep in mind, this exponent of 4/3 and this exponent of 8/3 is on the x only. It's not on the 2. Okay, this is 2 to the power 1 times x to the 4/3. So at the end, you cannot put this in parentheses. Okay, this power of 4 is on x only. This 10 is not going to change. All right, in a similar fashion, we will divide. 20 divided by 5 is 4. And when you divide same base, different exponents, you have to subtract. Now, you can turn any whole number into a fraction quite easily. I need to make this 4 become halves. So I think of it this way in my head. I don't always necessarily write this down, but 4 is how many halves? If you set it up like that, or at least think about it like that, 4 is how many halves? These two numbers that you say, you just multiply them. 4 is equal to 8 halves. So I can replace this 4 with an 8 halves. Now I've got 8 halves, subtract 3 halves, and that's 5 halves. And remember, again, that is the exponent on x, not on the 4. I'm not quite sure what I have this written here for. This would just illustrate to you that if you were to put this 4 back into a square root, it would have to become a 16. Okay, because the square root of 16 is 4. That's why I have this written here. And we're going to see some manipulation of things like this in the future. And finally, the last part of this section is what we call reducing the index of a radical. Now, the index of the radical is the root. And so lots of times, many times, you're going to want to simplify by reducing the index of the radical because it makes things easier. So here it says, you can simplify the task of simplifying radicals by reducing the index of that radical. This means that you are reducing or simplifying the rational exponent. Now keep in mind that when you have radicals, if the problem is given to you in radical form, you must give the answer in radical form. Yes, we're going to convert this to rational exponent form in order to simplify it, but then you must convert your answer back to radical form. If the original problem is given to you in rational exponent form, then you give the answer in rational exponent form. Radical form, answer in radical form. Rational exponent form, answer in rational exponent form. Like this problem from the previous page. It was given to us in rational exponent form. We give the answer in rational exponent form. This was just if we wanted to manipulate this 4, put it inside radical to give our answer in radical form. Because sometimes you are asked to give your answer in simplified radical form. So you do have to pay attention to the directions. This here, if you put this in rational exponent form and then simplify that rational or that fractional power, it's just a step, a go-between to help you make sense of it. So the 6th root of x to the 3rd power, I've got power over root. This becomes x to the 3 over 6, which simplifies to x to the 1/2, which simplifies to x to the power of 1. Root is 2. This particular problem here, I've got x to the 12th, and I want the 4th root of it. So power over root, this becomes base is x to the 12 over 4. 12 over 4, of course, is 3. keep in mind, this is an even root. Those are the ones that give us a tough time, and those are the ones we have to think about if we are using absolute value bars or not. Okay, so it's the even roots that give us that problem. The odd roots doesn't really matter. Okay, so we need the absolute value bars here. The fourth root of 7 squared, again, convert power over root, simplify the fraction. 7 to the 1/2 power is equivalent to the square root of 7. This one here can be a little tricky, and you will probably have a quiz question. I have this little star here with the word quiz. I'm sure you're going to have a quiz question. Now, notice that I've got 9 to the power 1 here. Okay, 9 to the power 1. And this is my variable x to the power of 2. And so what you're really doing is you're taking this 9 and asking yourself if you could rewrite 9 as some other base to the second power so that these powers match each other. And of course, we could do 3 squared x squared. Now these become exactly the same. 3 to the power over root, x to the power over root. Simplify each individual fraction. And since these are both now the fourth root of 3 and the fourth root of x, we could put them under the same one radical instead of having two things. Two different radicals written side by side. We want to write this as the 8th root of 9 times the 4th root of x. Okay, so keep that in mind. You will have one like that. And here I have another example that probably is not printed on your note sheet. Same type of deal here. I'm going to want to rewrite the 9. Well, I'm not going to be able to write 9 as some base to the 4th power. I could at least get it to be an even power, like this is an even power. Okay, so I'm going to rewrite this as 3 squared. I'm going to keep x to the 4th. And now I'm going to break it apart. This is 3 to the 2 over 6 power, x to the 4 over 6 power. I'm going to simplify the radicals. And notice they both have cube root. Okay, so it's going to be cube root of 3 to the power of 1 and the cube root of x to the power of 2. So since they are both cube root, I can put them both underneath the same radical, 3 to the power of 1, x to the power of 2. If you have any questions, please ask in class. Have a great day.